Hello. This presentation will be all about matrices, the different types of matrices, and the different types of operations on matrices. So first, let's have some terminologies with regards to matrices. So these are denoted as A equals A sub ij, and it's also enclosed in square brackets. And it's a rectangular array of numbers with m rows and n columns. So this is an example of a matrix. And as you can see, it has a lot of elements inside it. So it has m rows because there are m rows. So we are referring to this side. So this is the first row, second row, and then this is the mth row. And then for the columns, we are referring it from this side. So the first column, second column, and then the nth column, which gives you an n by n matrix. So hopefully that is an easy way to understand matrices. So again, the ith row refers to the first number when you're referring to a row in a matrix, and the jth column, which is represented by the second number in a matrix. So for example, if you have some element A, let's say 7, 9. So this refers to the seventh row, and 9 refers to the ninth column in some matrix. So that is the usual way of denoting elements inside a matrix. So what are the applications of this, at least for computer science? So it's used a lot in machine learning, specifically in linear regression in neural networks. And basically, a lot of the applications in machine learning heavily use matrices with regards to the equations that are being computed for. You can also see this in deep learning, specifically in image representation and processing, wherein you can represent matrices as images. So each um, number in the matrix represents the light, the lightness or darkness of a certain pixel in an image, at least for a grayscale image. You can also apply this as well to three or colored images rather. So red, green, and blue are used to denote the values in a colored image. And you can also use matrices to apply some filters or kernels to be able to enhance the features of a specific image that you have in mind. Additionally, matrices are heavily studied in linear algebra, where you can use this in linear equations, linear combinations, and other more concepts. So now let's delve into the matrix operations. So we have matrix addition, wherein the result is an m by n matrix, where A and B are m by n matrices. So what you're basically doing in matrix addition is you're basically adding them component-wise. So A11 and B11, when you add them together, you have an m by n matrix, and the first element, the sum, would be A sub 11 and B 1, 1. So it's basically component-wise. So another thing that you have to take note is that A and B must have the same dimensions in terms of their rows and columns. Otherwise, matrix addition would not work if their dimensions are different. So next, we have scalar multiplication, wherein it is an m by n matrix, where C times A is equal to every element in the matrix being multiplied by C, where C is any real number. So you're basically broadcasting the scalar to every element and multiplying them accordingly. So let's say we have a scalar C equals, let's say, 2, and our matrix A is equal to 2, 5, 1, and 3. So by applying scalar multiplication, what we get is 2 times 2, 2 times 5, 2 times 1, 2 times 3, where the 2 that we're multiplying is coming from the scalar C, which, when we simplify this matrix, it gives us 4, 10, 2, and 6. So that is the concept of scalar multiplication. Next is matrix multiplication, wherein it is an n by n matrix, where A is an m by k matrix and B is a k by n matrix. So before we proceed with how matrix multiplication works with an example, a very important thing to note is that when you are doing matrix multiplication, the number of columns of one matrix is equal to the number of rows in another matrix. So they must be equal for matrix multiplication to work. So let's say if you have, let's say, a 3 by 10 matrix multiplied to a 10 by 5 matrix, you would have a 3 by 5 matrix. And matrix multiplication is compatible because the number of columns of one matrix is equal to the number of rows in another matrix, and they must be equal. So let's say we altered the order of these matrices that we have over here. So let's say it became 10 by 5, and then we have 3 by 10. Here, matrix multiplication would not work because 5 and 3 are not equal. So the number of columns of the first matrix is not equal to the number of rows of the second, which would make this incompatible for matrix multiplication. Another way to say that it's not compatible is if we, let's say, have 5 by 5, and then we have 3 by 3. So this is also incompatible because the number of columns and rows are not equal. So it has to be equal for matrix multiplication to work. So matrix multiplication, each of its terms are formally defined as the following, wherein you have a summation of the product of A sub ix times B sub xj, wherein x is equal from 1 to k. So this formula may seem intimidating at first, but I will show here a simulation of matrix multiplication. So we have here matrix A, which is a 3 by 3 matrix, B, which is a 3 by 2 matrix, and AB, which is the product, which is a 3 by 2 matrix. So again, this would work because, once again, A is a 3 by 3 matrix, B is a 3 by 2 matrix, and since the number of columns here and the number of rows here are the same, then that means it's compatible, and therefore you could do matrix multiplication with this order, which would give you a 3 by 2 matrix. If you were to do something like B times A, that means that your dimensions will be 3 times 2 multiplied by 3 times a 3 by 3 matrix. And since the number of rows, columns rather, is not equal to the number of rows, then matrix multiplication would not work if you're doing it B times A. So A times B would work because of the equal number of columns with the number of rows. So let's define how each and every element is defined for the product matrix. So over here, we have A11 times B11. And then we continue on by multiplying A12 and B21. And then lastly, to get the final term, to get the sum, which is C11, we multiply A13 and B31. So notice that the direction that we're going for the first matrix A is going this way, and the direction of the second matrix B is going this way. So what we're doing basically is we are taking the multiplication or product rather of these, and then adding them all together to get C11. So that is how matrix multiplication works. So for the first matrix, you're going horizontally, and for the second matrix, you're going vertically downwards. So let's keep going to visually see the other products in the elements of the matrix C. So C12 is A11 and B12 added by A12 and B22 added by A13 and B32 together, which would give you this element C12 over here. So again, notice that you are again going horizontally and vertically. And you would notice this that um, another thing to take note is that when you actually do matrix multiplication, notice that the elements that you're pointing, when you sort of um, intersect them together, you would, it focuses on this element. So it's like multiplying it by here, and then you're sort of multiplying it downwards. So it's something like that. Uh, for you to be able to get the, or to be able to identify which element is being done, or you're trying to get the value of in matrix multiplication. So next is for C21, it's A11 times B11, A22 times B21, and then A23 times B31. So A21 times B12, A22 times B22, and A23 times B32. For element C31, you're multiplying it by taking the sum of the products of A31 and B11, A32 and B21, A33 and B31. And this also goes for the last element, A31 times B12, A32 times B22, and E33 times B32. So notice that when we are actually doing the matrix multiplication process, the elements need to also have the same row and column number. And you would also notice this in the other um, previous elements as well. So you could also see it here that they have the same row and column number. So that is another thing that you should also take note of when you're doing matrix multiplication. You need to ensure that the column number of the first um, element multiplied by the row of the second element in the second matrix are sort of, are have to be equal. Okay, so now let's try to apply this in an example. So given a matrix A and B, find the product of AB. So first things first, find the dimension of the product matrix. So A is a 1 by 3 matrix and B is a 3 by 2 matrix. And since the number of columns in A is equal to the number of rows in B, therefore the product matrix AB is equal to 1 by 2. Or that would rather be the dimensions. So next is we compute for the values of each matrix. So what we basically do here is follow the formula shown earlier, which denotes the formula to find for the elements in the product matrix. So first we have 5 times 1 multiplied, added by 4 times 3, and then 0 times 4. So again, we're going horizontally and uh, vertically downwards and horizontally to the right. So that's for the first element. For the second element, we are going to multiply 5 by 2, 4 by 2, and then 0 by 2. So again, horizontally to the right, then going downwards. So given that, that would give us the item over here. So AB is equal to 5 times 1 plus 4 times 3 plus 0 times 4. And then the second element is 5 times 2 plus 4 times 2 plus 0 times 2, which simplified gives you 17, 18. So next is the different other types of matrices that you may possibly encounter. So here we have the identity matrix, an n by n square matrix, I sub n, wherein delta sub ij is equal to 1 if I is equal to j, and 0 if I is not equal to j. So to visualize this, it basically tells us that, suppose we have this matrix over here, that if I is equal to j, or basically the row is equal to the column, it becomes a value of 1. So the diagonals, or the diagonal values of the matrix will have just 1. And for the rest would be 0 outside the diagonal. So all of this would be comprised of zeros. So that is how an identity matrix works. So how do you exactly apply this? Given the name identity matrix, it is similar to multiplying by 1 in multiplication. So if you multiply any number by 1, you get the same number. Similarly, if you are trying to multiply a matrix with the identity matrix, then you'll get the same matrix again. So how do we show that? So let's say we have a matrix A containing 2, 3, 8, and 11. And we want to multiply this to the square matrix uh, I sub n, or I sub 2, because this is a 2 by 2 matrix. So by doing so, the product matrix, which is AI, has the following result. So again, matrix multiplication will be applied here. So 2 times 1. So we're going this way and then downward. So next is 8 times 0. So we add that to here, which gives us the first element. Then the second element would be 2 times 8. 2, not 2 times 8, sorry. So this is 2 times 0. So this direction. So 2 times 0 plus 8 times 1. And then the last two elements would be 3 times 1. So that's 3 times 1. And then 11 times 0. And then for the fourth element, or the last element, it would be 3 times 0 plus 11 times 1. And by simplifying this, we get 2 times 1 plus 8 times 0, which is 2. 3 times 1 plus 11 times 0, 3. 2 times 0 plus 8 times 1, 8. And 3 times 0 plus 11 times 1, which is 11. Which gives us the exact same matrix as we have earlier, which is 2, 8, 3, 1, 11. So that is the identity matrix. So basically it acts as the you could think of this as like multiplying 1 to any number and you'll still get the same number. Next is the transpose matrix, which is an n by m matrix A raised to t, where the original matrix is an m by n matrix for I equals from 1 to m and from j equals 1 to n. So what you're basically doing in a transpose matrix is you're flipping the positions of the elements in the matrix. So, for example, we have some matrix over here. Let's call this B. And let's say we have 2, 3, 4, 1, 5, 6. When you're taking the transpose of a matrix, you're flipping for the dimensions as well. So this is a 3 by 2 matrix. The transpose of B is a 2 by 3 matrix. So we are expecting a matrix that looks like this. So with that in mind, how do we then make use of the values in B and put it in the transpose matrix? So first is to take note first on the diagonals. Since they have an equal number, equal in row and column number, then they won't change in terms of their position. So 2 is A11, so 2 goes here. 3 is 8, A sub 2, 2. Let's call this B instead. So this one is B11, B22, so it goes here. Next, for the non-diagonal values, we have over here B1, B21, row 2, column 1. So in a transpose matrix, this belongs then to B sub 1, 2, wherein it belongs in row 1, column 2. So that would then belong to, or would go over here. And then for the following succeeding values, so we have over here B sub 3, 1 becomes B sub 1, 3. And then for B sub 3, 2, it becomes B sub 2, 3. And then for B sub 1, 2, it becomes B, B sub 2, 1. Okay, so with that, we now have our new value. So B12 is where 4 belong to. So now we have 5, which now belongs in row 1, column 3. And then we have 1 belonging to row 2, column 1. And then for 6, it belongs to row 2, column 3. Sorry. 5 belongs actually to uh, row 1, column 3. So this is where 5 belongs, and this is where 6 should belong. So you're basically flipping their position. So notice that in here, 4 and 1 swap places. Yeah, so 4 and 1 swap places. And then another thing that you can see is that 5 went over here, and so did 6. So you can think of this, of transpose of a matrix. So let's say you have some matrix over here. Your transpose would look something like this. So you're basically flipping the dimensions, and all the elements that belong to this diagonal will stay the same. So that is an example of that would be 2 and 3 over here. So they just stay the same. Meanwhile, for the other elements that are not on the diagonal of the matrix, they basically swap positions. And even basically all values would swap in terms of their positions. So that is basically the idea for a transpose of a matrix. You can think of this as having a diagonal and you're sort of flipping all the values. So that is the concept of transpose of a matrix. So now we have an example over here. To find the transpose of a matrix given a 3 by 2 matrix A. So first is to find the dimension of the transpose matrix. Given that A is a 3 by 2 matrix again, therefore the transpose matrix would be 2 by 3 in dimension. And in constructing the transpose matrix, again, you flip the row and column number of the original matrix, swap them, which gives you the new row and column for the transpose matrix. So that is for this example. Next, if you have a square matrix, a 3 by 3 matrix, nothing would change in the dimensions because it's still 3 by 3. And in constructing the transpose matrix, we get something like this. So again, like I mentioned earlier, the elements at the diagonal don't change its position. So it's still 1 to 10 over here. Meanwhile, those outside the diagonal actually swap places. So 3 and 12 swap places. Then we also have 0 and 11 swapping places. And then we also have 4 and 7 swapping places. So that is some examples on how a transpose of a matrix works. Then we also have a symmetric matrix, wherein is square matrix is equal to its transpose counterpart, where A sub ij is equal to A sub ji for all I and j, where I and j are from 1 to n. So an example of this matrix would be, let's say we have 1, 2, 3, and then we have 4, 7, and 9. So this is a symmetric matrix. So if this is matrix A sub t would have the same values as well. Because aside from the values in the diagonal not changing, those outside of the diagonal will basically maintain the same or have the same number. So 4 over here would be swapped here, and then the 4 over here would go here. And since they have the same values, nothing would really change in terms of um the new values. So it's still 4. And then for 7, nothing also changes here. So the 7 goes here, the 7 also goes here. 9 also works that way. So they swap positions but don't really change in value. So you still have the same uh, matrix as the original one. So that means that A is a symmetric matrix. Another example of a symmetric matrix would be the identity matrix. So if we have, say, a square matrix I sub 3, wherein it's 1 and just zeros, if you try to find for its transpose, you're still getting the same matrix because the zeros just swap with each other. Meanwhile, the ones in the identity matrix at the diagonal will stay put. So the identity matrix is an example of a symmetric matrix as well. Next, we have the power of a square matrix, wherein you raise it to n, where it's raised to itself n times, or multiplied to itself n times. So if you have something like a squared, then you're basically multiplying the square matrix a times a. Then a cubed would be a times a times a. So the reason why it has to be square in particular is because if we attempt to do this on something that's not a square matrix, let's say we have a 3 by 2 by 3 a 3 by 2 matrix, and we multiply 3 by 2 matrices together, it will not already work on the first two matrices that you're trying to multiply because the number of rows is not equal to the number of columns rather is not equal to the number of rows. So it's incompatible and you cannot do matrix multiplication. Whereas if you have a square matrix, let's say a 3 by 3 one, you can multiply as many as you want because regardless, you have the same number of rows and columns here, which means it's compatible and you can apply matrix multiplication over here. So here are some exercises to practice on matrix operations. So here you have the 6 matrices of various dimensions, and you are to evaluate the following. So you can try this at your own pace and own time to be able to practice on the different types of operations and matrices. So now we have a different type of matrices, which are the 0, 1 matrices. So these matrices in particular are an n by n matrix whose entries are only either 0 or 1. So before that, it's basically a 0 and 1 matrix. So it just basically has any any order of zeros and ones in your matrix. So it doesn't have to be necessarily like an identity matrix, although it's an example of a 0, 1 matrix. But you can also refer to this as a Boolean matrix because it just has 0 or 1 values, which you can think of it as a true and false value. So it can also be of any dimension, and it also has its own set of special operations. So let's get into the operations of a 0, 1 matrix. So first we have the meet of a matrix. It's an m by n 0, 1 matrix where A and B are m by n 0, 1 matrices, and A and B is equal to 1 if A is equal to B, which are both equal to 1 and 0 if otherwise. So this meet operation, you can think of this as the logical and operator. Wherein if you remember from propositional logic, if you have two values, one is two propositional variables, and you take the and together, then you will get true if both of them are true. And it will become false if the rest are if one of them is not true or both of them are not true. So that is how this one would work in a meet of a matrix. So let's have a simple example. So let's say that E is 1 0 0 0 1 1, and suppose that B is A 0 0 1 1 1 1. So they both have to have the same dimension, like adding matrices. So they need to have the same dimensions. And taking the meet of a matrix would give us 1 and 0. So that becomes 0. 0 and 1 is 0. 1 and 1. So it's like, think of it as true and true. So that's true or 1. 0 and 0 is 0. So it's like saying false and false. No? And then we have 0 and 1, which is 0. And then 1 and 1, which is equal to 1. And that would become the meet of your matrix. So it's basically applying the logical and operator to each element of both matrices component element wise or component wise rather. Next is the join of a matrix, wherein, like the meet, it also needs to have the matrices be of the same dimension, and the resulting matrix would also be of the same dimension as well. Wherein A or B is equal to 0 if A and B are both equal to 0, and 1 if otherwise. So this, again, should be a familiar symbol, which is the logical or operator. So in a logical or operator, again, given two propositional variables, if you're trying to get for apply the or operator in two propositional variables, you get false if if both of them are false, and the rest would be true if there is at least one of them which are true. So that is how a joint of a matrix works. So how do you then apply that? So let's say we have, again, a matrix A, and then we have another matrix B. If we were to try to apply this by using the or joint of a matrix rather, so what we get here is the following. So 1 or 0 is 1, 0 or 0 is 0. And then 1 or 1 is 1, 0 or 0 is 0, 0 or 0 is 0, 1 or 1 is equal to 1. And that would give you this answer. So going back to the join and the terms itself, join and meet. So in here, the meet of a matrix is basically meeting two matrices that have ones. So those that don't sort of meet, like one is zero and then one is one, or both are zero rather, then you're sort of not meeting the matrices together. So it's like meeting two matrices which both have one in terms of the elements, and then the resulting element would be one. And then in the join of a matrix, you're sort of joining two matrices wherein if at least one of the elements is one, then the resulting matrix would be one. So you're sort of collecting the ones altogether in the join of a matrix, whereas in meet, you're sort of um, getting a result wherein each element that is one basically has matrix A and B have elements where both of them are one. And if either are or both are zero, then they won't exactly sort of meet, and the resulting would be element of at least in the meet of a matrix would be zero. So for the Boolean product, we have an m by n matrix where A is an m by k matrix and B is a k by n matrix. So this is similar to matrix multiplication wherein the number of columns is equal to the number of rows. And incompatibility can also happen if the number of columns is not equal to the number of rows. So here, this time, what we're doing is ANDing each term and then ORing them together. So if we were to shortcut this in a formula, in one formula, then we could have something like this. C sub ij is equal to the OR of the AND terms E sub ix and B sub xj from 1 to k. So an example of this would be, let's say, a matrix A, wherein it is 1, 0, 0, 0. And then we have matrix B, which is, no, let's make this a 2 by 3 matrix. So let's say this one is 1, 1, 0, 0, 1. So the Boolean product is going to be a 2 by 3 matrix because this one is 2 by 2, this one is 2 by 3. So the resulting matrix, since the number of columns is equal to the number of rows, it becomes 2 by 3, which comes from the 2 from here and the 3 from here. Okay, so now we apply the Boolean product. So in terms of direction, it's still the same. So we go here and then go here. Okay, so first we take the AND of A and B. So 1 and 1 is 1. Then you take the OR, so 0 and 1. So that becomes 0 because it's the AND of 0 and 1. So that becomes 0. Next is here. So 1 and 0 is 0. 0 or 0 and 0 is 0. Then for the third element, which is at row 1, column 3. So 1 and 1, so that becomes 1. 0 and 1 is 0. Then OR them together. For the element at the second row, first column, so we're now going to look at this row and then go back again at this column. So 0 and 1 is 0. 0 and 1 is 0. And then we proceed to the second row, second element. So 0 and 0 is 0. 0 and 0 is also 0. Then for second row, third element, we have 0 and 1, which is 0, 0 and 1, 0. So OR them together. And when you apply the OR operations, you'll get 1, 0, 0, 0, 1, 0. So that is how a Boolean product works. And here are some exercises to practice on 0, 1 matrices. So given these three matrices, you can evaluate the following over here and use these to practice on applying the Boolean operations on the 0, 1 matrices. So that is all for the concept of matrices. Thank you for listening.